Hello, we are going to go through 7.4 worksheet. One thing to do ahead of time is that we're going to apply inverse trig functions. So inverse trig looks like here's inverse tangent of some numbers of some value. I'm going to call it n. It's going to have a domain of all real numbers, and it's going to have a range from negative pi over 2 to pi over 2. These will help us come up with the answers here. Inverse sine of some value, it's going to have a domain of negative 1 to 1, which means the minimum value for sine inverse that we can plug in is negative 1, and the largest value we can plug in is 1. Anything less than negative 1, anything greater than negative or positive 1 results in undefined response here. And then the range, accordingly, will go from just like the previous one here, we're going to go from negative pi over 2 to pi over 2 inclusive here, so we're going to put square brackets here. And then finally, cosine is similar as far as what it looks like. The domain is the same. It can include and between negative 1 and positive 1. And the range here is inclusive 0 to pi. So keep that in mind as we work through these problems. We have some restrictions on the domain and range. So I'm going to change colors here a little bit. And again, I'm looking for what angle gives a sine value of 1/2. So I'm going to, in my mind, I'm going to whip up a little mini unit circle. 1/2 positive would be like here and here. And I only want the answer from here to here. So that's going to be 30 degrees. But with these problems, we want the radian measures. So we're going to call that pi over 6. Similarly here, cosine values are here and here. But again, I want from 0 to pi, so here is my range for answers. So that'll be 60 degrees, which is pi over 3. Now again, you could type these on your calculator. You will not get exact answers. Alrighty, in terms of the radians. Here, cosine of 2, or cosine inverse of 2, violates my domain, so we're going to say undefined, because it does not follow the domain for sine inverse, or cosine inverse. Now moving on here, positive root 2 over 2, that's going to be 45 degrees, which is pi over 4. Same thing here, because we know that at 45 degrees, it's root 2 over 2, comma root 2 over 2 for our ordered pairs. Remember, sine is our y value of the ordered pairs on the unit circle, and cosine is our x value. So pi over 4 here. Now negative is going to be either here or here, but again, the sine domain or range goes from here to here. So I want this one here, and that is going to be 7 pi over 4. But that's actually negative pi over 4 for our best answer. So we have to be careful. 7 pi over 4 makes sense, but again, we want this range from negative pi over 2 to positive pi over 2. So moving on here, this would be 90 degrees, which is pi over 2. This would be 0 degrees, which is just 0 radians. Cosine of negative 1 is over here. So that's going to be pi, 180 degrees if we want, but pi is our answer there. Moving on here, remember we did the tan values here. So root 3 over 3 is going to be 30 degrees. And that's going to be pi over 6. Because this really is 1 over root 3 simplified. Moving on here, this is going to be negative 30 degrees because of our range answer, which is negative pi over 6. Okay. And here again, sine inverse value of negative 2, it only can go as far down as negative 1, so this is undefined. Now if we wanted to graph what this looks like, here's my unit circle. And again, I'm looking at a point down here at negative 2, and you can see it's not on the unit circle, so that's why we stop. Now here, we're using your calculator, so you type, you hit second sine, type in this 5-digit, and you should get, in this case, 1.13889. Here, plug second cosine, negative, blah, blah, blah. We're going to get 2.75876. And again, these are in radians, so no degrees here. Here, likewise, we should get 0.88998. And here, again, this is larger than 1, so it's undefined or does not exist. Okay. So this is a bit different than what we've previously done here. Now, the one thing to remember that if I take the sine inverse of sine of 17 degrees, these cancel each other. These are inverse functions, and they're going to just leave behind what's in the parentheses. In this case, I use degrees. So with that in mind, since these are inverses to one another, my final answer here is just going to be 1/4, provided that the sine inverse is defined here. Over here, these cancel, and it's okay for tangent to be large, and this is just going to be 5. Okay, likewise here, we're in good shape. And away we go here, we get, that's going to be 1/2. That's 60 degrees. And then this one here, we get that. And negative pi over 6 is in our range for answers there. So we're just applying inverse functions onto the original functions itself. Now continuing on here, we have this. Now, it normally would give me 2 pi over 3, but this is not in our range, so I really have to think of this as the same. If I think about that, 2 pi over 3 is here. It's outside, so I have to kind of do a little subtract, and I'm going to think of coming up this way. So this ends up being negative pi over 3. So when we get something that's outside, we rewrite it with dealing with plus or minus pi. Okay, now this next one here, sine inverse of 1/2 gives me pi over 6. And the tangent at pi over 6 is going to be 1 over 3, or if we wanted to do it the long way, we get this. The 2's cancel. I get 1 over root 3, which gives me root 3 over 3. Okay. Kind of continuing here, we do this first part, sine inverse of root 3 over 2. This gives me pi over 3. And the cosine now of pi over 3 is going to be 1/2. And again, we just double check, make sure things are in the range of the function and or the inverse function here. So here we have sine of pi over 3 is going to be root 3 over 2. 2 times root 3 over 2 cancels that denominator 2, so I have the tangent inverse of root 3. Okay, and that is going to be pi over 3. Again, using our full-blown unit circle. Kind of continuing here. Again, just continuing on with more of these problems here. Again, Pythagorean triples are really important here. So if I go ahead and sketch my triangle here, it's a right triangle. Here's my angle. Cosine of this dotted angle would be 3 and 5. We have the 3, 4, 5 Pythagorean triple, which means this is 4. And now if I'm going to do the sine of this same angle, this would be 4 over 5. So we're using the inside part to develop a right triangle here. Moving on here, same thing here, right triangle. Here's my angle of interest for tangent. It would be 12 and 5. And we have a 5, 12, 13 right triangle, so that means that that's 13. So now I'm going to find the sine of that same dotted angle as being opposite over hypotenuse. Remember SOHCAHTOA. SOHCAHTOA is kind of something we're using here quite a bit. Moving on here, again we're going to have a right triangle. I've got my angle of interest here dotted. It's going to be 12 over 13. Looks like the previous problem. That means this is 5, which means cosine is going to be 5 over 13, but it's secant, so this is going to be 1 over cosine, so it's going to be 13 over 5. Tangent of 2. So again, if I go here, right angle, a tangent is opposite over adjacent. Now this is not a Pythagorean triple, but this length here is going to be the square root of 1 squared plus 2 squared using my Pythagorean theorem, so it's going to be the square root of 5. And as we kind of continue here, cosine is going to be the adjacent over the hypotenuse. And we normally cannot leave that in the denominator, that radical, so I'm going to rationalize by multiplying both by square root of 5, so I get root 5 over 5 for my answer. Continuing here, I'm going to work inside. Here's my angle of interest, adjacent, since it's cosine. Hypotenuse, this is a 3, 4, 5. I've got to double that. So I have to use my double angle theorem working through this. And again, it's the sine version, so sine of 2 of my dot is going to equal 2 sine of the dot times cosine of the dotted angle. So this is going to equal 2 times my sine is going to be 4/5, and cosine was 3/5. And so that's going to give me 8/24 over 25. So we'll kind of actually work there. Now here, this comes out to be pi over 3. This comes out to be pi over 6. Sine of all that. If I add the as common denominator, I have to do a little adjustment. So I got to multiply by 2, 2. So I get 2 pi plus pi. Switching back here, that's going to be the sine of 3 pi over 6, which is the sine of pi over 2, which is good old 1. Alrighty, so we've got kind of the clinical problems done here. Now let's take a look at some applied problems for 7.4. Again, here it's asking us to go ahead and they give us an image here of a space shuttle, and the fact that they want us to express the height as a function of the elevation theta. So I know that since I have an angle of interest theta, I've got the opposite and I've got the adjacent legs, and that's a right angle. I'm going to go ahead and apply the tangent function, and that's going to have to equal the tangent of theta equals h over 2. A little bit of work here, so now I've got to do my means extremes property. So I get h equals 2 times the tangent of theta. So, final answer, h is going to equal 2 times the tangent of theta. So again, here's what I was kind of working toward, and here's my trig ratio that helped me. Continuing here, now express the angle of elevation as a function of the height. So really I have h equals 2 tangent theta, and I want to solve for theta. So I'm going to divide both sides by 2. And now I've got to get rid of the tangent function by applying my inverse trig. So that looks like this. Oh, that should have been equal. So this is tangent inverse and tangent inverse. Now we know that this cancels that, so I get theta is going to equal tangent inverse of h over 2. And that is my function dealing with finding the angle knowing the 2 bits of information. Now similarly, this next problem kind of follows the same pattern here. Again, I've got an angle, I've got the opposite, I've got the adjacent, and so I've got tangent here. So the height is, well, here they ask the angle of elevation. So I'm going to say, hey, this is tangent of theta equals 50 over s, and we're talking feet. So again, if I apply inverse tangent on both sides, I'm going to get tangent inverse times 50 over s. I'm not too excited about using the variable s. Mine look like 5s all the time. Okay? Now they want us to actually do a calculation here. So they want us to find the angle of elevation. So that's the angle up from the horizon when the sun gives you a shadow with this pole of 20 feet long. So I'm looking for theta if I have a shadow of 20. So now we just type this in our calculator as it looks. If we're in radian mode, we're going to get 1.19 radians. If our calculator is in degree mode, we're going to get about 68.2 degrees. So again, those are both of our answers. Just be cognizant of what mode for angles your calculator is in. Similarly here, we're going to look for the express the angle as a function of the height. So my angle is going to be, now this time I have this, I've got the opposite, and I've got the hypotenuse. So this is going to be the sine. So this is going to lead me to the sine of theta over 1 equals h over 680. And so that's going to lead me to go ahead here and say h equals 680 times the sine of my angle. And now I've got to divide by 680 and sine inverse both sides, and that's going to equal my theta. So all of this for that. Okay? And then kind of moving on here, they want us to find the angle when the balloon's height is 500. So I'm just going to say, hey, the angle is now, height is 500, 680 for the height, and we type this in our calculator. And again, we're going to round it. If we're doing radians, we're going to get about 0.83 radians, or about 47.3 degrees for my answer here. Alrighty, well that concludes 7.4 worksheet solutions.